Let's examine the titration curve for the titration of a strong base by a strong acid. If you remember from example 3 of lecture 3, the titration of 20 milliliters of potassium hydroxide, a strong base, by 0.1400 molar nitric acid, a strong acid. And in that example, we learned that it took 15.81 milliliters of the titrant to reach the equivalence point, in other words, to exactly react with all of the potassium hydroxide initially present in the flask. We also learned that the original concentration of the potassium hydroxide in that flask was 0.1107 molar, and that the products of the reaction at the equivalence point, potassium ion and nitrate ion, would be expected to result in a pH equal to 7. Now, as in the previous two examples of titration curves, we could use a pH meter to monitor the pH as we added measured amounts of titrant to the flask, and it would look like this. If you compare this to our first example of a titration curve where we had a strong acid in the flask and a strong base in the burette, the pH here starts out quite high and then decreases as the titration proceeds, which of course should not be surprising since we're starting with a strong base in the flask and then slowly adding a strong acid. Now, as before, for the other two titration curves we covered in part 1 and part 2, we'll look at this titration curve and try to rationalize the pH values we see at 4 different points in the titration. We'll look at the initial pH, of course, before any titrant is added. We'll choose a point in the region between the initial pH and the equivalence point. We'll look at the pH at the equivalence point, and we'll look at the pH in the region beyond the equivalence point where excess titrant's been added. Now first, as we traditionally have done, we need to count how many potassium hydroxide formula units are in the 20 milliliters of solution in the flask before we add any nitric acid titrant. Well, we take the concentration multiplied by the volume, we get 2.214 times 10 to the minus 3 moles of potassium hydroxide. Now, since this is a strong base, we know that the initial contents in this flask are 2.214 times 10 to the minus 3 moles of hydroxide, 2.214 times 10 to the minus 3 moles of potassium ion, and of course, water. So the flask initially contains 2.214 times 10 to the minus 3 moles of hydroxide in a volume of 20 milliliters. So the concentration, of course, is 0.1107 molar. And so the pH would be 13.04, as we can see on the titration curve and on the table here. Well, how about between the initial pH and the equivalence point? We've chosen this point on the titration curve where we've added 7.14 milliliters of nitric acid. If you multiply by the concentration of that nitric acid, we can see that we've added 0.009996 moles of hydronium ion at this point in the titration. That hydronium ion, of course, reacts with hydroxide in the flask in a 1-to-1 ratio. So the number of moles of hydroxide remaining in the flask would be how many moles of hydroxide we started with minus the number of moles of hydroxide that have been reacted with the hydronium ion that was added from the burette. So the remaining hydroxide moles in the flask would be 0.00121144 moles in a total volume of 27.14 milliliters, which would give us this concentration of hydroxide. We can calculate then a pH of 12.65. At the equivalence point, you'll remember from example 3 and lecture 3, the pH should be 7 because the products of the reaction at the equivalence point are the neutral ions, potassium ion, and nitrate. We can actually get a pH of 7 directly from the titration curve by, first of all, consistent with what we've done before, we'll estimate the equivalence point as midway here in what is now a descent rather than a rise in pH. The equivalence point volume at that point, if you read it off the titration curve, I get 15.81 and a pH, equivalence point pH of 7. Finally, we can look at the pH in the region beyond the equivalence point. And as with the previous titrations, beyond the equivalence point, the pH is totally controlled by the number of moles of excess titrant, in this case, excess nitric acid, and of course the total volume. Now, the total number of moles of nitric acid added, or the total number of moles of hydronium ion, at the 23.43 milliliter mark in the titration curve would be the volume of that titrant added times its concentration for a total of 0.003280 moles of hydronium ion. The excess hydronium ion now in that flask would be the total number added minus the number of hydronium ions that we needed to reach the equivalence point. And this would be the leaving, I should say, the number of moles of excess hydronium ion in the flask. So if we take that excess hydronium ion divide by the total volume at that point, we get a concentration of hydronium ion of 0.02455, which would give us a pH of 1.61. Well, how about indicator selection? As with the previous two titrations, we can overlay our choice of indicators for the strong base titrated by the strong acid case from lecture 3 right on the titration curve. Recall once again that we choose indicators that give us an endpoint as close to the equivalence point as possible. The titrant volume at the endpoint minus the titrant volume at the equivalence point would be the titration error, so we want to minimize the titration error. Note that both phenolphthalein and bromethymol blue seem to introduce minimal titration errors. And again, what we mean by that is that if you look at the middle of the transition for the color change for phenolphthalein on the steep descent and for the bromethymol blue, both of those would give volume of titrant on the x-axis, values for that volume of titrant, very close, if not pretty much identical to the volume at the equivalence point. So they would minimize the titration error. Using phenolphthalein here in this steep descent portion is fine, although recall that phenolphthalein loses a little bit of its luster here because the transition now is from a color, pink, to colorless, which is not as easy to pick up as the transition for the titration of the acid, which would give you colorless to pink. In lecture 3, we left you with a question of what 2 other indicators might be possible. Both thymo blue and methyl red seem to be okay here. They both appear in this steep descent portion, although you'd have the challenge with those of deciphering when one color went to another.